Welcome to my channel, where we explore the mysteries of the universe. Today, we dive into one of the most intriguing and awe-inspiring phenomena in astrophysics: black holes. These cosmic giants have captivated scientists and the public alike for decades. But did you know that even the greatest minds in history struggled to accept their existence? Albert Einstein, the father of relativity, and his contemporaries were irrationally resistant to the concept of black holes. Why? Because black holes are not just any astronomical objects. They represent the ultimate boundary of our understanding, a place where the laws of physics break down. Let's take a journey back in time to see why these brilliant scientists found black holes so hard to swallow. All stars must eventually die, but their fates vary dramatically. A star like our Sun will shrink into a dense white dwarf. Larger stars might collapse into neutron stars, ultra-dense remnants where gravity is so strong it warps time and space. But for the most massive stars, their death leads to a transformation into something that defies our understanding: a black hole. When a massive star collapses, it creates a gravitational vortex so powerful that not even light can escape. This is a black hole. It distorts the fabric of the universe, creating a region of space where the laws of physics as we know them cease to exist. The story of black holes began over a century ago. In 1915, while on the front lines of World War I, Karl Schwarzschild provided solutions to Einstein's field equations, revealing that under certain conditions, a star could collapse indefinitely, forming what we now know as a black hole. Yet, even Einstein found this idea troubling. Einstein's theory of general relativity showed how massive objects curve space-time, creating gravity. But the concept of a singularity, a point where gravity becomes infinite and space-time curves infinitely, was too extreme for many, including Einstein himself. He and other prominent scientists like Sir Arthur Eddington resisted the idea for decades. It wasn't until the 1960s that the existence of black holes began to find acceptance, thanks to the work of astronomers and new technology. Today, we have actual images of black holes, like those captured by the Event Horizon Telescope, proving that these enigmatic objects exist. Now, we believe black holes sit at the heart of most galaxies, including our own Milky Way. This means there could be billions of black holes scattered across the cosmos. But the journey wasn't easy. In the 1930s, a young Subramanian Chandrasekhar calculated the fate of dying stars, showing that those slightly more massive than the Sun would collapse into something denser, leading to the concept of black holes. His ideas were initially met with resistance, but he persevered and eventually won a Nobel Prize for his work. In 1939, Robert Oppenheimer and his colleagues published a groundbreaking paper describing black holes as real stellar phenomena. However, the advent of World War II shifted his focus to the Manhattan Project, and the paper was largely forgotten at the time. Today, we continue to study black holes, unraveling their mysteries and discovering their impact on the universe. They challenge our understanding and push the boundaries of physics. But more importantly, they inspire us to ask questions and seek answers about the very nature of reality. Let's delve deeper into the intriguing history and the developments that led us to our current understanding of black holes. We begin with Einstein and his revolutionary theory of general relativity. In 1915, Albert Einstein presented a new theory of gravity. Unlike Newton's law of universal gravitation, which described gravity as a force between masses, Einstein proposed that gravity is the result of masses bending the fabric of space-time. Imagine space-time as a two-dimensional rubber sheet. When a mass, like a planet or star, is placed on this sheet, it creates a depression or curve. Other objects moving nearby are affected by this curvature. This visualization helps us understand how gravity works according to Einstein's theory. It is the curvature of space-time that tells objects how to move, and the objects tell space-time how to curve. Enter Karl Schwarzschild, a German physicist and soldier serving on the front lines of World War I. Despite the dire circumstances, Schwarzschild read Einstein's papers and made a groundbreaking contribution. In a letter to Einstein, He provided the first exact solution to the field equations of general relativity. This solution described the gravitational field outside a spherical, non-rotating mass such as a star. Schwarzschild's solution revealed a remarkable feature, a radius, now known as the Schwarzschild radius, below which a star's gravitational pull would become so strong that not even light could escape. This was the theoretical birth of the black hole. However, Schwarzschild himself did not fully grasp the implications of his discovery and saw it more as a mathematical curiosity. Einstein, though appreciative of Schwarzschild's work, was uneasy with the idea of singularities, points where quantities become infinite. He believed such extreme scenarios did not exist in physical reality. This discomfort was shared by other leading scientists of the time, like Sir Arthur Eddington. Eddington was a prominent British astronomer who played a crucial role in popularizing Einstein's theory of relativity in the English-speaking world. In 1919, he led an expedition to observe a solar eclipse, providing the first empirical evidence that the sun's gravity could bend light from distant stars. This observation confirmed a key prediction of general relativity and catapulted Einstein to international fame. Despite his contributions to relativity, Eddington was skeptical about the idea of black holes. He argued that no known physical process could lead to such an extreme state of collapse. Eddington's influential stance slowed the acceptance of black holes for decades. Meanwhile, young Subrahmanyan Chandrasekhar was making significant strides. During a voyage from India to England in 1930, he calculated that a star of a certain mass, beyond the Chandrasekhar limit, could not end its life as a white dwarf. Instead, it would continue to collapse under its own gravity. This was a crucial step towards understanding black holes. Chandrasekhar's findings were met with strong opposition from Eddington, who dismissed the idea of such catastrophic stellar collapse. Eddington's public criticism at a 1935 conference was so influential that it discouraged further exploration of black holes for many years. In 1939, Robert Oppenheimer and his colleague Hartland Snyder published a paper that described the formation of black holes in a more concrete way. They showed that when a sufficiently massive star exhausts its nuclear fuel, it will undergo an unstoppable gravitational collapse, forming a black hole. However, the outbreak of World War II and Oppenheimer's subsequent involvement in the Manhattan Project diverted attention from this groundbreaking work. It wasn't until the 1960s that the scientific community began to seriously consider the reality of black holes. Advancements in radio astronomy and the discovery of quasars, a type of extremely luminous active galactic nucleus, provided indirect evidence for the existence of black holes. These objects emitted vast amounts of energy, which could only be explained by matter falling into a supermassive black hole. The turning point came with the development of advanced telescopes and observational techniques. In 2019, the Event Horizon Telescope captured the first ever image of a black hole in the galaxy M87, providing direct visual evidence of these enigmatic objects. This image showed the shadow of a black hole, surrounded by a bright ring of light emitted by superheated material falling into it. Today, our understanding of black holes continues to evolve. We now know that black holes come in various sizes, from stellar mass black holes, formed by the collapse of massive stars, to supermassive black holes that reside at the centers of galaxies, including our own Milky Way. These cosmic giants play a crucial role in the evolution of galaxies and the universe as a whole. Scientists are also exploring the possibility of intermediate mass black holes, which could bridge the gap between stellar mass and supermassive black holes. Additionally, the study of black hole mergers, detected through gravitational waves by observatories like LIGO and Virgo, provides new insights into these mysterious objects. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as merging black holes. These waves carry information about the events that produce them, allowing scientists to study black holes in a completely new way. The first detection of gravitational waves in 2015 confirmed a major prediction of Einstein's theory of general relativity and opened up a new era of astronomy. Black holes challenge our understanding of the fundamental laws of physics. They are natural laboratories for testing theories of gravity, quantum mechanics, and the nature of space-time. The singularity at the center of a black hole, where density and gravity become infinite, remains one of the greatest mysteries in science. It suggests that our current theories are incomplete and that a new, more comprehensive theory of quantum gravity is needed. Physicists are working on various approaches to unify general relativity and quantum mechanics. One such approach is string theory, which proposes that the fundamental constituents of the universe are not point particles but tiny vibrating strings. Another approach is loop quantum gravity, which suggests that spacetime itself has a discrete granular structure. These theories aim to provide a deeper understanding of black holes and the nature of singularities. Black holes also play a significant role in the large-scale structure and evolution of the universe. They influence the formation and growth of galaxies, regulate the flow of matter and energy, and drive powerful jets that can impact their surroundings. By studying black holes, we gain insights into the processes that shape the cosmos and our place within it. So, what do black holes teach us about the universe and ourselves? They remind us of the vastness and complexity of the cosmos, the limits of our knowledge, and the endless possibilities for discovery. They inspire us to ask big questions, to seek answers beyond the horizon of what we currently understand, and to embrace the mysteries that make our universe so fascinating. We invite you to join us on this journey of exploration and wonder. What do you think? Are black holes the key to unlocking the secrets of the universe? Let us know in the comments below. Don't forget to like, share, and subscribe for more fascinating insights into the world of science and space. Until next time, keep looking up and stay curious.